Hello. In this unit, we're going to cover two fairly widely used SGD algorithms, RMSProp and ADAM. And I'm going to try to provide some theoretical background and useful conceptual framework for these algorithms. RMSProp and ADAM are adaptive. And what they do is they take each particular parameter value and use a different learning rate for each parameter value. And the learning rate that's used for the parameter value is computed from statistics for that particular parameter value. ADAM is a variant of RMSProp. RMSProp is sort of the fundamental idea, and then ADAM provides a little bit more structure, and ADAM has become much more widely used than RMSProp. So I'm going to start by discussing RMSProp because it's really the fundamental idea. So RMSProp was introduced in class lecture notes by Hinton. If you look it up and look for the reference, they reference Hinton's lecture notes from a course he was teaching. Inspires me a little bit. Okay, so RMSProp is based on a running average of the squared value of the gradient of a particular parameter. So if you look at a particular scalar parameter, the gradient of the loss with respect to that parameter is a scalar. And we're writing that scalar as the gradient estimate for parameter I. And we're going to take a running average of the square of that particular parameter gradient estimate. So this is the running average equation. So this is the running average of the square. It's a convex combination. And I'm using the rolling average parameterization of the running average. So this is sort of the effective window size of a rolling average, of a corresponding rolling average. So this is taking a convex combination of itself and the next thing that it's incorporating into the running average. And this window size is typically 100 or 1,000. So that corresponds to this number being 0.99 or 0.999. And then we use this update. So I've computed this running average of the square. I take the square root of that and then add some constant to prevent this from going to infinity if this was 0. And then I use that whole quantity as the learning rate for this particular parameter, right? So we're getting a different effective learning rate for each particular scalar value of the parameter. Now there's something that's a little bit theoretically interesting here. RMSProp is using an estimate of the sum of the squares. Well, the sum of the squares is not the same as the standard deviation, because the standard deviation takes the sum of the differences between the value and the mean. So the sum of the squares is called the second moment, which is different from the variance. If the mean is small, right? If you're near an optimum, the total gradient is going to be very small. So near an optimum, the average gradient should be 0 because you should be not moving that much. Or at an optimum, the average gradient is 0, stationary point. If the average gradient is 0, there's no difference between the second moment and the mean. So it's not clear how important this particular artifact of RMSProp is. But if you go to PyTorch, PyTorch does have a centering option which divides by the standard deviation rather than the square root of the second moment. I just want to say a little bit about the possible theoretical motivations for RMSProp. So when we did our temperature analysis, the stochastic differential equation computed the stationary distributions of SGD, we got a formula like this, that if you use sort of vanilla SGD, the probability density, that is the stationary density under this stochastic differential equation model, has this form in a fairly general setting. If we assume that the loss function is locally quadratic and positive definite at a local optimum, and we work in a coordinate system where we've picked the coordinates such that that quadratic basis is isotropic, is just the identity matrix of the Hessian is just the identity matrix. Then you can write in this fairly general setting, you can write the stationary distribution in this form. So it's proportional to the exponential of the sum over the individual parameter coordinates of the square of that particular parameter value divided by a kind of temperature, but where the temperature depends on the parameter. It depends on the variance of the gradient of that parameter. So it's not a Gibbs distribution because it's using a different temperature at each parameter. But if we use a different learning rate at each parameter, we can correct for that and convert it to a Gibbs distribution. So if we simply use a learning rate at the parameter that divides by the standard deviation, then we get a Gibbs distribution. And intuitively, this Gibbs distribution is sort of desirable because it means the stationary distribution is exploring sort of evenly all of the place where the loss function is low. And in Hinton's original introduction of RMSProp, he introduced it as a kind of exploration mechanism. He wants to increase the probability that we explore that space, or the rate at which we explore the space effectively. However, this analysis has problems. It assumes that we've converted to a coordinate system where the Hessian is the identity matrix, and that's really hard to do. And so we're doing this in the wrong coordinate system. Also, even when you center RMSProp has the PyTorch implementation has a centering option that lets you get the actual standard deviation rather than the square root of the second moment. In that case, even if it's centered, RMSProp is dividing by the standard deviation rather than the variance. And this is theoretically mysterious. Almost any, I've done two or three anyway, attempts at theoretically deriving RMSProp. Why does this work? Can you prove a theorem that justifies it? And inevitably, whenever I prove a theorem, I get this form, dividing by the variance. But empirically, what RMSProp does seems to be working better. And I just want to maybe give an intuition why this always comes out of the theory. And that has to do with units. If you use this formula, then it turns out that the units for eta is just 1 over the loss function. And if you use this formula, eta has to have more complex units. Depends on the choice of whatever weight unit you're using for the parameters. So based on just dimension analysis, you can see why any theoretical analysis is going to tend to produce this. The units are correct, or more correct, whereas this thing has problematic units and you just can't get that out of a theorem. But this seems to work better in practice. Part of the mystery of deep learning. ADAM, adaptive momentum, ADAM. ADAM combines momentum and RMSProp. Now, in PyTorch, the PyTorch version of RMSProp also supports momentum. However, it's presumably the standard form of momentum, and I've discussed in previous units how the standard formulation of momentum creates a coupling between the momentum parameter and the learning rate. You have to adjust for momentum to get with the learning rate to get a constant temperature, to maintain your temperature schedule. So RMSProp may be suffering in terms of its popularity and usage by this inadvertent coupling between two of its parameters, which makes the hyperparameter tuning problematic, right? When you change one, you have to change the other. ADAM uses a momentum parameter that is naturally decoupled from the learning rate. So the temperature, you can change ADAM's momentum parameter and the temperature of the SGD doesn't change. So ADAM is much more popular. And it's not completely clear why, but I conjecture that it's just a big part of it, maybe this simple phenomenon that RMSProp hasn't properly decoupled momentum from temperature, whereas ADAM has. ADAM also has another feature called bias correction, and we'll talk about what that is right now. So ADAM uses momentum and RMSProp. Both momentum and RMSProp involve running averages. Momentum involves a running average of the gradient estimates, and RMSProp involves a running average of the squares of the gradient estimates at each parameter. Now, if you define a running average this way, the initialization is problematic, right? Because you initialize it to 0, and then it's taking a running average, which is analogous to a rolling average over n elements, but you're starting at 0. That means there's this warm-up period. So as you know, until you get large compared to n, until that running average starts to make the initialization look invisible, you've got this huge bias towards 0. So it's not clear to me that this is a big deal because you're going to run long compared to n anyway. However, ADAM has bias correction. It makes that initial run-up not initialized to 0, but it maintains a local running average. So let's look at so how do I efficiently maintain a running average that's the running average of everything I've seen, right? So I want to, instead of making a running average of just the last n, I want to make it a running average of everything I've seen. So this simple update maintains a running average of everything you've seen, right? If this is a running average of everything you've seen up to time t-1, then if I multiply by t-1 and divide by t and add 1 over t to the next one, I get the average of the first t as computed from the average of the first t-1. So this equation will compute the average of the first t from the average of the first t-1. And this can be rewritten this way, right? This is just the same as 1 minus 1 over t plus 1 over t. So it is a convex combination of the same form that we use in a running average, but the t is increasing with time. Now this is going to stop being a running average when t gets large compared to n. So there's this simple thing you can do. You just take this convex combination and you make this the min of n and t, right? So up until n, you're getting running average of everything you've seen so far. And once you get to n, you switch to the running average that's analogous to the rolling average over n. In the published version, and presumably in the implementation of ADAM, there's a much more obscure form of this bias correction that amounts to the same thing. This is a very simple implementation of bias correction. So here's the ADAM algorithm, right? You're doing a running average of the gradient. This is the momentum, but it's defined as a running average, and that eliminates the coupling of the momentum parameter to the temperature of the SGD. So this is the sane way to do momentum in terms of a running average. It's also doing the running average of the square of the gradient, which is we discussed with RMSProp, and then it's doing the RMSProp update. So it's got the same momentum, it's got the debiasing, but other than that, it's just RMSProp. Now, here's the update equation. Now, this has two hyperparameters. It's got the learning rate hyperparameter. It has the epsilon hyperparameter here. And the epsilon was introduced to prevent this from ever being infinite. But in practice, it's often the case that when you tune both of these, you get a large epsilon. And if you get a large enough epsilon, the epsilon will start to dominate this sum for many parameter values. And that seems to be important in a lot of uses of this. And it's nice for other reasons, which I'll mention in a moment. So the optimum value of epsilon is often large. And for large epsilon, it is useful to reparameterize this by taking eta equals epsilon times some eta 0. And if you reparameterize it this way, then this equation can be rewritten like this. And the advantage of rewriting it this way, with eta defined slightly differently, is that if you take epsilon to be large, take epsilon to infinity, such that this becomes small, we can take epsilon to infinity, and this reduces to, this becomes standard SGD while holding eta naught fixed, right? So if epsilon is large, this form decouples the meaning of the learning rate parameter from epsilon. So you always want to make your hyperparameters independently optimizable. You don't want to have these strong interactions where if you move this one, you have to move that one. So this reduces the interaction between epsilon and eta. Okay, so there's another thing we might want to worry about. It's nice if your optimization algorithm does not have to be retuned. You don't have to retune your metaparameters when you change your batch size. So can we make ADAM independent of the batch size? And that turns out to be tricky. So this is what ADAM actually, this is the computing the rolling average, running average of the square of the gradient value for some particular parameter. Now this thing, G hat in PyTorch, is defined to be the average over the batch of the gradient estimate. And if you take the square of the average, that's not the same as taking the average of the square. The average will tend to reduce, if the average is large enough, you're going to get almost exactly the mean. And the square of the mean is not the same as the average square. There's a variance in between those. There's a gap, which is the variance. So if we're gonna get good estimate of this quantity per instance, right, per training instance, we would rather do this, right? We would rather sum up over the batch the square. But the code, I always run into this problem that the code doesn't support what I want to do. In PyTorch, this is difficult because optimizers, the general concept of an optimizer in PyTorch is defined to be a function of G hat T. So G hat T does not contain the information you want, which is this. So to compute this, we would need to maintain a batch index at the gradient attribute of the parameters. So I think there's another issue with ADAM in that it's sensitive to batch size. Okay, next unit we're going to go back to a little more theory of SGD, and then we're going to move on to generalization. Thank you.